In this video, we'll be exploring the concentration and changes over time for reactions. To do this, I'm going to walk through each order of reaction you have to know and the properties associated with that order. With that out of the way, let's begin. Starting off, we have a 0th order reaction. Remember that the general equation for writing the rate law for any reaction is the following, with N and M representing the orders of our species. By the way, all the following reactions we're going to be talking about are single species reactions, and we're going to be talking about the decay of a single substance. So we're only going to be using the concentration of one species, in this case, A. Forget about B for now. So if we have a 0th order reaction, that means that our species are all raised to a 0, thus making our rate equal to just K. Next, we have the integrated rate law for a 0th order reaction. The integrated rate law is the equation which relates the concentration of our reactant to time. It's derived by performing calculus operations on our rate law. But you won't be expected to do any calculus on the AP exam, so this rate law will be given you on your formula sheet. The integrated rate law for our 0th order reaction is as follows. Again, don't worry about memorizing that, it's going to be on the AP chemistry reference sheet. Something you might also have noticed, this equation is very similar to our y equals mx plus b, and we can actually put it on a graph. When we plot this on our time versus concentration of A, we will get a straight line, and the slope of this line is going to equal our negative rate constant, negative K, which we can identify from our equation. Now the reason all this is important is because it can help us identify the reaction order for our reactant even when it's not given to us. For instance, say that we don't know the reaction order for A, but we are given this graph for A. Well, if we have this graph, if we see a negative slope when we plot the concentration of A against time, then we know that it must be a 0th order reaction. And so that's very important. You need to make sure you know how to identify the reaction order based off your given graph. Additionally, we can use this to predict the reactant and product concentrations at specific times. How will we do that? We're just going to be using this equation over here. You can plug in your rate constant and your time and your initial concentration, and that will let us solve for a final concentration. So again, just make sure you're comfortable using this equation. The last thing you have to know for a 0th order reaction is how to find its half-life. The half-life of something is the time it takes for any amount of any substance to decrease by half. So for instance, the time it takes 0.4 molar H2O2 to reduce into 0.2 molar H2O2 would be its concentration half-life, because this value is decreasing by half. To find the half-life for a 0th order reaction, you take the starting concentration of your species, that's the concentration of A, and you divide it by twice the rate constant, so by 2K, and that will equal T1/2, which is how we signify half-life. An important thing to notice about the half-life for 0th order reactions is that depending at which time we start on our graph, we are starting with a different concentration of A. For instance, at this lower time, the concentration of A is much higher than at our greater time, where we have a smaller concentration of A. Thus, because our denominator stays constant and our numerator is constantly changing, we do not have a constant half-life for 0th order reactions. For a 0th order reaction, our half-life is dependent on our initial concentration, and it's super important you know this. And so these three properties, your half-life, your integrated rate law, and your graph, are what you have to know for 0th order reactions. Now, for 1st order reactions. For our 1st order reaction, the rate is going to equal our rate constant times our reactant this time, because we're raising it to the 1st power, so that's not going to turn into a 1. Our integrated rate law for a 1st order reaction is as follows. As you can see, this differs from the 0th rate law, because our simplest graph for a 1st order reaction is not going to be a straight line. If we simply graph the concentration of A versus our time, like we just did with 0th order reactions, we're going to end up with a negative exponential curve, which is good to know, but it's not as useful for our calculations. Generally, we like having that straight line. To get our straight line, all we have to do is take the natural log of our reactant. And doing that, again, we get our straight line with our slope equal to the negative rate constant. And so again, this is a concept you absolutely have to understand, and it's why we need integrated rate laws in the first place. If we don't know the order of our reaction, but we plot its concentration versus its time, and we get a straight line, then it must be 0th order. If we plot its natural log concentration versus time, and then we get a straight line, then it must be 1st order. like we see down here. Make sure that you can identify the order of a reaction based off this property, because it will most certainly be tested. And again, using our integrated rate law equation, if we plug in our rate constant, our time, and our concentration of reactant at that time, then you can find the concentration of our reactant at a specific time. Again, that's why this equation is so useful. Another thing you could do, if you know your final concentration, your initial concentration, and you know your rate constant, then you could solve for the time it took to get there. You can solve for the time it took to get from a starting concentration to an ending concentration. Let's say we mark that as X on the graph. Again, that's why these things are so useful, because these are questions that are going to be tested. And if you'd like me to make a video over that in the future, just let me know. Also, as you can probably tell, because I'm drawing this on the graph the whole time, you can completely use the graph for this as well, if it's giving you points which are easy enough to read. Lastly, how do we find the half-life for a first order reaction? Again, this formula is going to be on your AP chemistry sheet, and it reads T1/2, that is our half-life, equals 0.693 over K, our rate constant. What's very interesting about this half-life, and what's different from the half-life for all our other ordered reactions, is that it's always going to be the exact same length. Because this 0.693 is a constant, and our rate law, K, is also a constant, defined by our equation. And so again, what this means, it's going to take the exact same time for 1 molar of an isotope to reduce to 0.5 molar as 0.5 molar of a first order isotope to reduce to 0.25 molar, even though we have to reduce twice the amount in the first scenario. Because it's a first order, the half-life is constant. Again, make sure you can identify reaction order based off of this property. And then to finish off this video, let's look at second order reactions. For this one, the rate law is going to read K, our rate constant, times our reactant squared. The integrated rate law reads as follows. As we saw with first order reactions, if we just plot the concentration of our reactant versus our time, we're going to get a curve. If we plot the natural log for the concentration of our reactant, we're still going to be left with a curve. That's still not going to give us a straight line. We're only going to get that straight line when we plot 1 over the concentration of A against time. And this time, we're actually going to end up with a straight line with a slope of positive K. Finally, to find the half-life for a second order reaction, we use the following formula. Half-life will equal 1 over our rate constant times the initial concentration of A. Again, as with our 0th order reaction, the length of our half-life is going to be changing depending on our initial concentration of A. So just make sure you know that as well for your second order half-lives. And so those are all the properties you have to know for the change in concentration over time for different ordered reactions. Just for a quick recap, you need to make sure you're able to find the half-life for any reactant for these orders. Additionally, you should be able to identify which order a reaction is going to be based on the graph given to you. You should also be able to draw an approximate graph based on your order. It doesn't have to be perfect, you just have to know whether to draw a curve or a line. And then lastly, using your given integrated rate laws, you should be able to solve for the concentration at a certain time, or the time it takes to get to a certain concentration for your reactant A. Again, if you're confused about this and you'd like me to make a video over it, please just let me know. And with that being said, that's all you have to know for concentration and change over time for AP Chemistry. I know that this was a lot of information to take in at once, and it might have felt confusing. If that's the case, I recommend rewatching parts of the video. If it's still not making sense, take a break and come back after. Thank you for watching.